Hello everyone, welcome back to our minute concepts on chemistry, particularly on the topic of chemical kinetics. And this time we're going to be talking about half-lives, particularly half-life rate laws. Now, what is a half-life? A half-life is the duration of time that it takes for any substance to get cut in half, or not exactly cut in half, but be half of its original. So let's say that I had 4 moles of a substance, or 4 molar of a substance, and after one half-life, it would be divided by 2, it would be 2 molar. Now after another half-life, it would be divided by 2 again, it would become 1 molar. Then again, then again, then again and again and again and again, until the substance is essentially gone, and it approaches 0. Now, a half-life can be described in this way. So the amount of substance after a certain amount of half-lives is given by the original amount of substance. So for this, we're going to be using concentration. The initial concentration of a substance times 1/2 to the power of the number of half-lives, where n is the number of half-lives. Okay, so let's say that in an example, our initial concentration is 4, and we let it sit for 2 half-lives. So that would be equal to 4 times 1 over 2 to the power of 2, which is 1/4. And this would mean that we would have a final answer of 1 molar, because these would cancel out. And that's how we use that. Now, of course, we can reverse engineer this. We can say, for example, that we don't know the amount of half-lives. We don't know the amount of half-lives, but we do know that it's equal to 1 molar. Like after a certain amount of time, it's equal to 1 molar. Well, what we can do here is we can divide both sides by 4, so that we are left with 1/2 the power of n here on the left side, and we could apply common log. So, well, while not exactly necessary, this is the formal way of solving for this. So taking the log of 1/2 to the power of n, we would be getting the log of 1/4. This is going to be equal to n log 1/2 is equal to log 1/4, which we can then further rearrange to get n. So n would be equal to log 1/4 over the log of 1/2. And that should get you an answer of 2. So that's very similar to how we solve for the order of a reaction. Of a reactant rather. So this is one half-life formula you should be familiar with. Again, we use this formula to solve for the final concentration. Let's indicate that here, shall we? Let's put this equal to F. There. So this is our first half-life equation that we're going to be using for this video. Now next are the half-life rate laws. Okay, so these are just our regular integrated rate laws. Right, those are our integrated rate laws. Now, how do we modify these to become half-life rate laws? Well, modifying these would make this video a bit long. But essentially, it's just deriving or further simplifying all of these in terms of T when the final concentration is equal to the initial concentration over 2. So in other words, if you substitute the the final concentration using this term to all of these equations, you can simplify it in terms of T to find and get our half-life rate laws. And doing that, we would actually get the following. So for zero order, first and second. For zero order, our rate law is given by the initial concentration over 2k, or 2 times the rate constant. For a first order, it's going to be the natural log of 2 over k. And lastly, for second order, it's going to be 1 over the rate constant times the initial concentration. Like I mentioned in the last video, understanding the relationship between the concentration and the rate of an equation of a reaction is slightly clearer when we look at it through its half-life rate laws. So as you can see here, let's actually spread this out a bit. So in the first rate law of a half-life, first order, we can actually see that there's no relation here between the concentration and the half-life. Now, why is that? Now, if you recall, the rate constant actually doesn't even have concentration in it. This is 1 minus 1. So it's actually just s to the power of negative 1. In the first place, our rate constant doesn't take into account concentration. So let that be your first giveaway on why it doesn't involve concentration here. Now, how about for our zero order? Also, an implication of that here for first order reactions is that regardless of the concentration, it will always be the same for any substance. So for any concentration of any substance, the half-life would be the same. Now for the zero and second, it does take into account the concentrations, and they're actually very resemblant of their own integrated rate laws. So those should be pretty straightforward. We just use them in the same way that we would our regular integrated rate laws. So perhaps another video to fully understand the derivation and the explanation. But as I mentioned earlier, to get this, all you have to do is substitute the initial concentration divided by 2 for the final concentration in all of our integrated rate laws. So these are our half-life equations. So we're going to actually put this to the side. We're going to put this like right up here, just so that we have them as our like guidance, I'd say, our basis. Oops, if I can just select all of these. Okay, there. Okay, now these are our half-life equations. These are all equal to T, by the way. Alright, so how does this work? Well, obviously, since it's equal to T, we use it to solve for time. Now, on various occasions, we'll be asked to derive other parts of this equation. So it could be, for example, the initial concentration or the rate constant. So let's give it a shot with our last used rate law in the last video. So in the last video, we determined that the rate law for that experimental data was actually K times the concentration of A to the power of 1. That makes it a first order equation. First order expression, reaction. So if let's say our rate constant this time, we're not gonna use the same one as the last video because I kind of forgot what it was. Let's say that our rate constant here is 0.5 per second. All I have to do is do the natural log of 2 over 0.5, and that would be our half-life for this reaction. So plugging that into our calculator, we would actually be able to get 2 divided by zero point 0.5. We would have a half-life of 1.38, or rather 1.4 seconds. Well, actually, this isn't even a correct significant figure set, so this would be 1 second, roughly. Now, what does that mean? That means for every 1 second that passes, our substance A is half, which is actually quite crazy for a half-life. So I guess you would see this in rapidly decaying substances, radioactive substances. So yeah, keep in mind that everything has a half-life. It just sometimes it just is really long. And where do we normally see half-lives? We see it in carbon dating, or we actually even see it in some medical exams. They actually use radioactive elements to highlight different parts of your body, and these elements have half-lives that allow it to decay naturally within your body. So obviously they have to be safe in the first place in order for us to use them in medical application. But anyway, that's just some trivia for you guys. Now, where do we go from here? Well, really, that's it. For the first order reactions, that's literally just it. Now, let's say that we're going to solve for, let's say we'd want to solve for K. So let's back up a bit, and let's say that for our first order reaction, we were given a half-life of 60 seconds, and we want to figure out what K is. So it would just be ln2 over K is equal to 60. Now, rearranging that, we would get K is equal to ln2 over 60. So now, what's the answer to this? ln2 divided by 60 would be 0.0. Let's just put this here. This would be equal to 0.0115, so on and so forth. And this would rounding off to one significant figure. That's just 0.01 per second. So let that put into perspective how we would be using all of these others. So we can actually give those others a shot. Okay, so let's try. Let's try using a zero order reaction. So let's say that our initial is equal to 5 molar, and our T is equal to 4 minutes. What is going to be the rate constant in seconds? So now it's a bit different because we're given the answer in minutes and we want it in seconds. So how do we approach this? Well, let's be a zero order reaction. So here, let's just plug in our values. So this is, again, rewriting first 2K is equal to T. This means that our equation would be 5 over 2K is equal to 4 minutes. However, we want it in seconds, right? So we need to convert minutes into seconds. There's 60 seconds every minute. So writing it this way would allow us to cancel our units. So cancel, we're left with 240 seconds. It's equal to 5 over 2K. Now, continuing our derivation, we would have to multiply 2K to both sides to cancel out the K on the left. So we would have 480K is equal to 5. And to isolate K, we divide 5 by 480K. Or rather 480. And that would be equal to 0.01 0.01, hold on, I'm running out of space. 0.01 Now, what's the unit for a zero order reaction? Again, the units for any order reaction is just m to the power of 1 minus n times s to the power of negative 1. So here, our overall order is 0, so it would be n to the power of 1 minus 0 times s to the power of negative 1, or just n to the power of 1 minus s minus 1, s to the power of minus 1. So this is thus m over s, 0.01 molar per second. And that is our rate constant for this problem. So that essentially wraps up how we use the rate laws of half-lives. And they all really behave the same way. Again, this is just a mathematical, well, all integrated rate laws in general are used to mathematically represent what is happening, what is the relationship between the concentration of a certain substance as well as its rate of reaction. And understanding the basics of, well, this is linear algebra, understanding how to manipulate an expression is actually all you need to solve for the rate of reaction using rate laws. In half-lives especially, you just need a basic understanding of how to use logarithms, for example, to derive for n, or regardless if you need to derive for n, just derive anything really that's present in the equation. All you have to do is plug and play and move the terms around. So again, to just quick recap, half-lives are the amount of times that a substance was halved, while a half-life with an F is how long it takes for a substance to be half of its original amount. And every substance has a half-life. And what else? There are 3 main half-life rate laws derived from the original integrated rate laws by substituting the initial concentration divided by 2 for the term of final concentration. So actually, I highly suggest you guys try to derive it yourselves as well to get to the answers or the equations that we used here. That would really improve your understanding of the equation. And what else? We manipulate the half-life equations based on the given so that we can solve for either the time or rate constant. And that wraps it up. So I hope you guys learned something from this video. It's actually quite quick in comparison to our last video, at least, because this topic is really not very hard. It's just sometimes it's very analytical when it comes to tests. So you need to observe and understand what's being laid out in front of you first before you start solving. Maybe you might misinterpret some terms or some numbers that they give you. Just make sure that whatever you're reading, you read it correctly, take it slow, and practice so that you can understand how to identify what certain problems you're looking for, and you can make sure to get it right 99% of the time. So that's all. Thank you everyone so much for watching, and I hope you guys again learned something. This is, I think, the last topic that we have before moving on to our next set of topics on equilibrium. So thank you everyone, and I hope you guys learned something. I'll see you all in the next video. Goodbye.